I want to do something a little bit crazy today. I wanted to try to do a unification of theories. And I wanted to try to take quantum mechanics, quantum mechanics, which basically is about wave functions. And we find these wave functions in Hilbert spaces. I can make it a fancy H or something. But these are Hilbert spaces, um, which are going to be shaped like six-dimensional Calabi-Yau manifolds. So we'll get into sort of more detail about all this stuff. Um, After that, what we need to do is essentially project the information in this complex space, because this six-dimensional volume is essentially three complex dimensions, right? And we're trying to project this information into the real world. So there's a convex Hall wave function which connects quantum points, the entanglement lines together. And this configuration creates a flux which sends the spin information through the 11th dimension, which is imaginary time. And so we make this projection. We're making a projection of this information across the imaginary time dimension. I know this sounds a little crazy, but what we're doing is essentially a Wick rotation. Okay, and for this works in a lot of different situations. Okay, and the projection goes from the six dimensions across the imaginary time into 3-1 space-time Wick rotation. Okay, so let's see if we could describe this a little bit more specifically. The Wick rotation is going to be this idea that we can take time and we can just call it imaginary time instead. And this gives us access to a lot of different things because, well, imaginary time, the imaginary complex plane, I guess, the imaginary axis is tangent. Okay, this is tangent, which means 90 degrees tangent to every point in 3-1 spacetime. Okay, where we kind of have the regular time here, real time, and then we have this XYZ here, which gives us the volume. And so we kind of have this four-dimensional space-time that we use. Whereas over here, we're getting things like the complex coordinates, which would be something more like this. We would just call it like the Z's. We could say Z1, Z2, Z3. These are complex numbers. I'll just kind of try to do that real quick. Z1, and we want three of these Z's. Instead of calling it XYZ, we're calling it Z1, Z2, and Z3. These are essentially basis vectors. It's really more like complex basis vectors. And these complex basis vectors are, of course, they come from the C3 over here. They're elements of C3, the complex manifold, something like this. Um, Consider that this is a Calabi-Yau manifold. And what we can do is we can essentially project this across the 11th dimension, which is imaginary time, and then send us back into real time and space. We can sort of write that out sort of like this. Here's our wave function x, y, z, t, and that just comes from this integral m, and this is the manifold. It's an integral across the manifold. Okay, let me do that. We essentially get the same thing, but, well, what we're doing is we're going to encode the information on this side, and it's going to come out on this side. Okay, it's basically a little transform that you can do. We're going to call this again z1, z2, z3. Okay, here's a little coordinate. Put it right here. And we have e to the negative I, and here's the energy. And of course, you also need time. So we're basically using the imaginary time here to encode the information across the six-dimensional manifold. Okay, and this is, of course, going to be the seventh dimension of the complex dimension. So we sort of have a total of 7 on this side here, 7 dimensions. And we also have 4 dimensions over here. I mean, so you can see where the 11 dimensions come from. Okay. So if we can relate quantum mechanics in this 11-dimensional thing that's happening here, we need to call upon string theory. Because string theory is essentially, we got to ask ourselves, okay, what the heck are these wave functions? Where are they again? Well, they're in these Calabi-Yau manifolds in this Hilbert space. This is Hilbert space. Okay, now this stuff just comes from quantum mechanics because we're just using the wave function here. But let's take a quick moment over here to consider quantum states as points in Hilbert space. Okay, points in Hilbert space. So these points here are essentially they're a complex, they are a quantum state. That's what that point is. It's a quantum state. In fact, we can just connect this right here. Quantum state point that's in that Hilbert space. Everything's making sense so far. I mean, this is just normal uh, quantum mechanics, complex wave function. Okay, so now the idea is we have entanglement lines. Okay, so we have points, then we have lines, and the lines represent entanglement, which is how the points can connect together. Alright, and I'm just going to double check something real quick here. Make sure I'm not going too crazy. But we're getting close to something here. We're about to connect things together a little bit better. Alright, let's get to the third level of the cohomology. This is essentially cohomology right here, which kind of describes how points and lines, and then the third level is the wave function convex hull. And this is basically going to connect all the points in line together and make a little area. So put a point there. Here's a couple different points with a line in between. Like that. And then, of course, if you have more, then you get a convex hull. This little area in between there. And this is essentially the wave function. But let's realize that the boundaries of the wave functions the boundaries are essentially going to be this the boundaries like right here, right? I made it kind of a triangular one just so we could get the idea. But let's realize that these wave functions are more circular, right? They look something more like this. Okay, let's make it more something like that. Okay, the boundaries of the wave functions. Now it's kind of crazy what's going to happen in this little mess here is because when we start wrapping these things around, we start wrapping this around the dimensions of this Hilbert space, wrapping around the Hilbert space dimensions, multi-dimensional, really, it's this whole 11-dimensional system. Well, it's really more of a 6-dimensional Hilbert space that this is wrapping around. It's kind of hard to get this idea, but it's a 6-dimensional space that this wave function sort of wrapping around as a convex hull. And the boundaries were strings. Strings, meaning the strings from string theory. You know, these are essentially loops of energy. Loops of energy. Yeah. And the reason why they're one-dimensional strings, keep in mind that kind of like, well, how did we go from, 6 dimensions down to 1 dimension? Really, this convex hull can be represented as a 2-dimensional area. So let's put a slight thing here. We call it more like a 2-dimensional area. Well, maybe, let's not call it 2-dimensional area, although it should be. But essentially, we shrink it down to 1 dimension, and that's what happens um, when we compactify these things. Let me just kind of get this a little bit straighter. Basically, you get a one-dimensional loop from a uh, higher dimensional process. Let's try to examine how that happens. Mm, let's consider cycles. I'm gonna get more into details here. Cycles. At the string, and these are going to be, I guess, closed paths. That's exactly what this is here. You can wrap these around multiple times. So you're going to have sort of like this n cycles, which equals one cycle, take the one form. You need to really get this straight here. And sometimes it's a little bit harder to represent things mathematically. So let's just kind of get through this. Okay, so this is a one cycle. We have to use this y here. Oh, this is a one cycle. Okay, this is the one cycle. One cycle. Okay, you could think of it as like from here all the way to there. In fact, I'll label this purple because that is the path it's taking all the way around. Okay, so we get this by integrating across a one form. We call it W. Uh, discuss forms are a little bit complicated, so we might have to discuss that a little bit later. But let's just focus on sort of getting through this whole idea and try to flesh out some more details later. Okay, so then we have to deal with the fluxes. So this is how we get sort of strings by wrapping around um, multiple times. You can take a sort of a rate. So mm, yeah. So you get two kinds of radii here. We'll call it like a big radius, and then you can also call it a 1 over r, a small radius. This is essentially what T-Duality is all about. I guess I'll make this one back over here. Let's discuss T-Duality, where you can take r and 1 over r, and the idea is that these are both the same, uh, the same, the same energy. So we can say something like this: E squared equals n squared, oh my gosh, n squared over r plus mr. Can't really just take energy and turn it into, sorry, radiuses and turn it into energy, but is indeed proportional. Let's say it's proportional, so. Let's see if we can show modular transformations here. This might make a little bit more sense. It's not easy to get this first. Hold on a second. So T-duality, let's consider what S-duality is as well. There are these two forms of dualities across these strings. And the S-duality is going to be, let's take a modular transformation here, which goes t plus 1, and then on this side, I'm going to try to get this down so we can get into the next piece of this whole puzzle. This is T-duality, and when we do this, I'm going to screw it up here. Negative 1 over tau. These are the two different types of modular transformations. Modular transformations allow for these two types of dualities which tells us that big radius strings are essentially the same thing as small radius strings. And essentially what we're doing here is we're taking a Fourier transform of the spectra. So we have momentum and we have position. So we can switch between the two when we're trying to describe these wave functions and these strings. We can describe them as in terms of momentum or in terms of position. When you get a bigger radius, it gives you more momentum. When you have a smaller radius, you get more position. And that's how these two are linked. And so you could describe the same. Basically, what you're doing is you're trying to describe the same wave function. By using this superposition of momentum and position. And so, essentially, what T-duality is superposition duality, right? The idea that you have a big radius wave function, but uh, in momentum terms, it's dominated by the momentum quantum states. Well, you could start making it smaller, wrapping it up and stuff, and you could describe it with the smaller radius. But in that case, you have to use position. So we're describing the same wave function by using the superposition duality, which is described by this modular transformation. This tau thing is essentially, I believe that's the imaginary time right there. Not imaginary time, but let's just see. Try to explain how we're getting this imaginary time out of all this. Let's just kind of real quickly take a look at this Wick rotation that we're doing. String theory. Let's come back to that. We kind of connected it here from quantum mechanics. We get boundaries of wave functions, which can essentially be those strings there. There's two things we need to do. First, let's relate imaginary time to all this. All right, we have Minkowski space, the metric, Minkowski metric, which is going to be negative, positive, positive, and positive when we're doing um, four-dimensional space-time. We have to represent time as negative because it just acts different from space. So time is just very different from space. So yeah, quite separated. I mean, we could say it's negative space, but whatever. So time is just not really equal to space. It's tangent, in a sense, 90 degrees. And if we go ahead and keep in mind that the Minkowski metric involves the ds squared, which involves taking ct squared plus x, well, dx squared plus dy squared plus dz squared. And if we translate that into imaginary time, do believe there's a negative sign right here. Yeah? So if we translate this into imaginary time, then we get the Euclidean metric, which just makes this positive. Well, why did we just make this positive? Because we made it imaginary time, so it's no longer regular time, it's more imaginary time, which is much more equivalent to space. Okay, so this imaginary time dimension, which is much more like space, because it's positive. And in fact, if you take the metric right, we get that positive because you took the metric and we made this TIT. And when you do that, you're going to get a -1. You square it. So this is essentially going to turn positive. And so there we go. Right? So we have this imaginary time dimension, which we popped out right there. This is how we can do the modular transformation. We need a dimension to do modular transformation. Because the M theory, 11-dimensional M theory, is essentially uses this time dimension to do these modular transformations. Just kind of scoot this over a tiny bit here, over here. Let's take a look at those modular transformations again. The 11-dimensional M theory needs to use this 11th dimension. Well, M theory uses the 11th dimensional to do modular transformations. And so this 11th dimension, as we've seen, is just simply the imaginary time, which is required to do this Wick rotation here, this projection from this complex volume into the 4-dimensional. Well, we do this through this imaginary time dimension. Now let's continue this situation where we managed to get flux configurations. So let's go ahead and now figure out what these flux configurations are. So the 11 dimensions, the imaginary time is the 11th dimension. Let's just get that straight. And across this, we can pass information. Okay. Specifically the information spin info superposition stuff, entanglement stuff. We can send charge, mass, all sorts of stuff. So spin, charge, those kinds of things. Um, you can even say mass here. Different types of information get passed through this 11th dimension. This quantum information that's encoded when these strings vibrate. So essentially, the surface area loops around to form fluxes. Here's a loop, and we can send the flux through that. Alright, there's a lot of lines going through there, but it's essentially that's the flux information. Yeah. Here's the flux information. Surface area loops around and forms flux configurations. Flux configurations encode the data. They send the data across this flux, and it's this information here. And here's how we can represent that with reform integral. You're going to get a flux from the reforms. What the heck are these? Oh, this is a one cycle. This is a three cycles. This is the three cycle here. I'm gonna make it in blue. Or really more of the complex. It's the complex three form that we're using here. F3. This is the one. This is the one form from the one cycle, and this is the three form. And this is the three cycle. It's kind of like, what the heck do these words even mean? Um, it's a little bit more about like cohomology and stuff. We're sort of, this is, I believe this is a one form. I think the one form is this line here. I think a two form is an area. The three form is a volume. So that's why we get this volume by using the surface area. I think it's kind of complicated stuff here. Let's so the field strength of free form. We kind of really have to get in like major nitty-gritty details to explain what these one forms and these three forms and the two forms are. Well, let's throw the two form in there. This is a called Lamond. This is just a name. This is a called Lamond field. B, and this is a two form. Couples to the world sheet of the string. Sexiest field is described by the field strength three form. H is the three form, just this. Integrating this three form over the three cycle gives you the flux. It's the flux. Three cycle and the three form. Yeah, three forms. I mean, this all makes sense here, kind of. I mean, you need one forms, two forms, and three forms. The one forms are going to be just the one cycles. The two forms are going to be two cycles, I believe. I think the two cycle. Two form field B. I think we're getting a little closer here. Keep in mind, we need a world sheet for string theory. So we need the world sheet. And we're going to have space. And we're going to have time. Right, so we have this. This is a two form. And so we have this B field. B is going to be equal to this is the field equation for the Cohomology field. So 1/2. Then we have B mu V down here. Components of the field. And then we have to just integrate that across dx in the mu, and we have to pair it with the dx in the v. And this is a two form because we're taking two dimensions. Integrating them all together, this couples to the world sheet. Now we have a string action now. doing, let's see, sheet, space and time. This stuff here, which is West Zumino. West Zumino string action. Let's write it in a really complex form right here. We get the integral of the sum of the d space and time, integrating space and time here. And then we have the energy. What the heck is this energy? Oh, sorry, the antisymmetric tensor. Oh my god. I'm just gonna put that right there. This is just the string action. Not exactly 100% sure about how to calculate all the string action here, but the idea is that we have a derivative with respect to this A, new direction, combined with the derivative with respect to B, B direction. This stuff here. We just have the B mu V. Something like this. So this is West string action. Fluxes. So this here is flux. Okay, the three form happens, when you get all these loops and cycles everywhere, you get all these fluxes pointing in all these different directions. And so those are essentially how we're able to pass the information across that time dimension. Because we're trying to put information from complex volume to real volume. Let's now move into S-Duality, because we realized how this is West string action. What's Zeno WZ term? I think we're getting a little bit confused between, the total action. That's the West Zumina action. Then we also have S Polyakov. Yes. Right here, the total action is going to be equal to the sum of the Polyakov plus the sum of the West Zumina term. So I think we had the one sub here. Okay, okay. And now we have the Polyakov action, which we will put as it's going to be. It's going to be the same form-ish, but this time it's the Polyakov action. Right, so this one's a little bit weirder, and I didn't make this stuff up, alright? 1 minus 4 pi. Oh, this is the reggae slope. Oh my god. So we have the reggae slope, which has to deal with the scattering amplitudes. Sweet. And then we have this blah 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 time. So I don't think we have E in this particular version. I think they changed it to an H. H. And this is actually the determinant. It's the determinant of the world sheet metric. Some stuff we can understand, some stuff we can't. Then we have negative H square rooted, clearly. And then we have the H, and then we have the derivative. So we're doing this across the world sheet, also two-dimensional. And I see how this is not coupled because you add them together, you couple them. So we took the world sheet metric and we coupled it with the fields here, the Karl-Brayman fields. And the fluxes came from The thing is, we went from a two form into a three form. Oh, okay, so we have F, this F, the F here is three form. It's actually just the derivative of this field. And that's how we're able to go from the two form to the three form. Exterior derivative. Exterior derivative. Now, exterior derivative. Okay, so anyway, we have now connected the idea that these one-dimensional strings come from wrapping around these wave functions. Well, the boundaries of these wave functions are really the strings. Um, and that these flux configurations come from wrapping around the wave function into these little loops that send fluxes through them. We can interpret that flux as being that imaginary dimension of time which passes the information through. And the vibrations of these strings are essentially the action here. Vibrations of, in fact, let's call it more to really drive this home. Oscillations of wave function boundaries as the fluxes pass through them. Those oscillations are string actions, string vibrations. And let's not call them strings, okay? These are circular loops of energy. Okay, this is the purple stuff. Just make it perfect. Circular loop of energy. Because that is your string. We can't use point. We can't use points because points of energy, uh, points of energy, points of energy in basically in zero volume, because it's just a point, it's a singularity. So you can't do that. And so that's why we need these circular loops of energies. And, well, you can see how these wave functions are just convex holes. They're just, combining all the quantum points and the entanglement lines together. And they're just sending the information through those fluxes. That's how we're able to project the information from these well, 6 or 7 dimensions, depending on whether you count this imaginary time here. This is the 7th dimension. There's the 6 complex space volume. These are just basis vectors, so you can twist them around in any direction you really want. So they're all just basis vectors. And sending that info through into the 4-dimensional spacetime. Let's take a look at S-Duality, because we were discussing how these modular transformations are able to show you again how the wave function string theory here, this is really just a description. Okay, string theory. Let's now define it really. It's sort of a description of the interactions between wave function boundaries. Okay, so these wave functions have boundaries, and this large dimensional surface area, when you try to flatten that down into this one dimension, you essentially compactify this information into one dimension. So what are these interactions? What are these interactions? Well, so the oscillating boundaries, or rather it's oscillating amplitudes, yeah? Okay, oscillating amplitudes, which are the boundaries. And then we have superposition duality, and then we have entanglement duality. Superposition duality and entanglement duality. Superposition duality, entanglement duality. Superposition duality comes from being able to describe the same wave function and its boundary as being momentum or position, giving you either a large radius or a small radius. And the modular transformation happens like that through basically this rotation's happening in imaginary time. So these are all rotations in the IT dimension. Okay? Considering that e to the I theta is just equal to 1, in a sense. So you can kind of use this sort of idea here. So you can put whatever angle you want in here, and it always equals 1, so you can do rotations and just multiplying by 1. Okay, so let's do S-Duality. Okay, so we have the string coupling constant, GS. We can flip that around to 1 over GS. So this is what S-Duality is. This is the string coupling constant. And what that essentially means is entanglement. Okay, you either have weak entanglement or you have strong entanglement. And, well, this is just trying to describe how if you have, really strong coupling, then you have a strong entanglement. You have weak coupling, you have weak entanglement, those kinds of things. Maybe the opposite, but I think this is the gauge coupling. Yeah, this stuff is pretty good. I mean, I could keep throwing in like little equations of how like we're just like adding one or flipping things, but it's just pretty self-evident at this point. This is entanglement duality. We can express the same wave function using either strong or weak entanglement, depending on whether you use a stronger or weaker coupling constant. Okay, and so now, yeah, it's basically, we can see why we can see why there we go, there we go, there we go. Okay, perfect. We can see why the boundaries of string, why the wave functions are boundaries of strings. They're just describing superposition and entanglement. Radius of the wave function, larger radius, smaller radius of the wave function, entanglement of the wave functions, stronger, weaker entanglement. It's just the different dualities of the M theory. And yeah, so these wave functions, they just wrap around, send these fluxes through. The information passes down. It gets sent over in this projection here. Now, let's go back to this whole thing. quantum state points, entanglement lines. So all this stuff kind of happens within a Hilbert space. All right. All this stuff happens within a Hilbert space. You have this. It turns out we're going to go into loop quantum gravity. We're going to show how the Hilbert spaces are essentially at every point in spacetime, right? They form this tangent manifold at each particular point. And it's a complex manifold, of course. But, again, we have the idea that the Hilbert spaces can form quantum points themselves. Really quantum states. And then they also have entanglement between spaces. This is in fact called the spin network. Quantum states come from the nodes, which are their own local Hilbert space. And then we have the entanglement between spaces. You can see how H total is tensor product of all the Hilbert spaces at each one of these points. Just call it, well, I'll call it heat. Alright, Hilbert spaces at each one of these points. Tensor product them together, you get the entanglement between the spaces. This whole thing creates the spin network. This is where the fluxes of info can pass. Entanglement happens through imaginary space, by the way, imaginary time. And the reason for that, just take one quick moment here to describe what entanglement really means. We have 2 points which receive the same info, or well, info simultaneously, really. Across spacetime. Or how can that happen? Well, the imaginary time dimension is tangent to every point. So as soon as you go into imaginary time, you can reach every other point in spacetime. So IT literally gives you access to all spacetime. Okay, to the whole universe simultaneously. If you step into that IT dimension, you have access to the whole universe. You can take another step out. So that's how information can basically go through the imaginary time dimension. That's what this entanglement is saying. And that the fluxes between these spaces. I just need to show. So flux info goes through imaginary time. That's the entanglement dimension. Okay. Now we have to deal with entropy. Let's go down imaginary time. And let's go to the infinity. Let's take it to infinity. Alright. Let's start with the wave function imaginary time. Set that equal to E. And we have the negative Hamiltonian. And then we put tau here. Put the wave function. Time evolution is described by this. I guess we have the initial state right here. Okay, yeah, so this is just the initial state. At time 0, and then we can send that transformation through, take this to infinity. I'm going to basically t goes to infinity, and then what happens is uh, here to describe this. But essentially, this takes us to the lowest energy point. So, just give me a moment here to iron this out again. Alright, so I think what happens here, we get this interesting, just want to show this because at least we can understand this, and we could say that we have coefficients, called green coefficients here. There's one associated with E naught, where this is just the energies. It's T, and it leaves us with the zero eigenstate. Well, this is the eigenstate, is the energy here, and zero is the ground state. Okay, and we could start doing this over and over again, because we can get another one over here, and call this C1, but I'll just call it Cn, because there's going to be a zillion of these, and we're just going all the way to infinity. Here's the end. Now, as this number, so let's say E naught is HC or something, or HF, and this is more like, I think, NHF. Let's go check this. It's not that simple. There's like there's a more complicated formula. It's more like N plus half HW. H bar W. H bar W. Okay. So anyway, we get higher energy as you go up in energy levels, and you get just HW for the energy knowledge. Let's check. Wait, please. Yes, we get 1/2 H bar W for the first energy level. Alright, so that's going to be the ground state. And as we take time to infinity, or imaginary time to infinity, then what happens with the exponent? This is an exponential decay equation. And since it's an exponential decay, As these exponents get larger, you're just shrinking away. Uh, you're just making the ground state. You're just making it, all the states are decaying to the ground state as fast as they possibly can. So this is fast decay, and this is slow decay. So you're doing something to normalize the wave function. Essentially what this is saying is that over a long period of time, over a long period of imaginary time, only the lowest energy is going to remain. So long, we could just say E naught remains. T goes to 1, only only the ground state remains. This is just a principle of quantum mechanics. If we go down imaginary time, only the ground state remains. And we usually do that using a Wick rotation by just substituting the wave function with imaginary time instead of regular time. And let's quickly rewrite the Schrodinger equation. We can see if we take the derivative of imaginary time, or the partial derivative. You know, I'm not just going crazy here. That the Schrodinger equation itself is written like this. Here, there's the Schrodinger equation. Let's put it right here real quick. That right here real quick. So we have I h bar partial wave function xt, and then we have to divide this by partial t. Well, what are we doing here? But taking the partial of imaginary time. What? Well, yeah, so that's basically, that's what we're doing with the Schrodinger equation, and we get the Hamiltonian acting upon the wave function. So yeah, basically, the stuff happening in imaginary time causes stuff to happen in real spacetime. So those rotations, those dualities that were rotating around here, these transformations through imaginary time, this this information encoding, the flux information sent through imaginary time, entanglement through imaginary time, all of this is basically a rotation happening in imaginary time, and that makes the wave function do stuff. So now the wave function does stuff. Basically, just keeps cycling back and forth. But see that this is all just one cohesive theory. It's all the same thing. We're not done yet. We still have to finish the loop quantum gravity. Now we've realized that entanglement happens through across this imaginary time, and the spin network entangles all these Hilbert spaces together. And now let's see how entanglement entropy comes from minimizing the surface area of the entanglement states. All right, so let's look over here for a moment, and let's get to the density. Density matrix A. This is equal to the trace of B. Traces out the degrees of freedom in B. And we have a wave function that we're splitting into two, essentially. So kind of signifying entanglement. So entanglement entropy for A is SA equals negative, we have to take the negative trace, and we're taking this, and then we have log this, and that gives us entanglement entropy. Now, what the hell is PA? I think it's entanglement density. some density matrix here. A density matrix. Say it's like entanglement density kind of, but there's more than just entanglement. So it's not. This is more just the reduced density matrix. But anyway, so we get this entanglement entropy for A using trace of this reduced density matrix. And so let's look at the Ryu Takayanagi formula, which says that SA, well, hold on a second. Yeah, I think it's the same SA. And that's that's going to be equal to the area. We're discussing this YA. It's a minimal surface area. And we have to divide that by 4 times the gravitational constant. Let's minimize the area using optimization. Minimizing the area. So we could say interval and this is the determinant of the induced metric. Hmm. Basically, what we're saying is that minimizing area leads to curvature. This is the metric. Metric tensor? Um, Yeah. Bulk metric. So we have the bulk metric. Let's take a look at what the bulk metric is. The bulk metric of anti-de Sitter space. Right, de Sitter. Anti-de Sitter space. We're going to have this ds squared equals GUV, and we have dx dx. Oh my god. This is just a line element. Um I think we do something crazy. Jesus Christ. This is insane. Let's just focus on getting it all kind of makes sense, but it's like just one second, one second, one second. Let's write this out. The same thing as saying like L squared over R squared. And then we have negative d t squared plus dr squared plus dx squared. So this is just going to be a comparison of L radius and anti-de Sitter radius, which is the L radius, and then the radial coordinate. This happens in anti-de Sitter space, which is where this spin network exists. One second. Well, not in anti-de Sitter space, but the bulk here is like n plus 1 n plus 1 dimensional anti-de Sitter space. This is what the bulk is referring to. And it has constant negative curvature. boundary, these quantum state nodes are associated with a volume. These edges the entanglement edges between spaces form an area. Okay. Here's the spin network. And the spin network evolves over time. Minimal surface in the bulk. There's the bulk. Minimizing the area in the bulk. Minimizing the area in the bulk. Yeah. Okay. So now we have entanglement entropy. Just this. You Nagi. Entropy A. So this gives us, by essentially minimizing the entanglement distances, this area that's formed is basically entanglement paths. And we want to minimize the entanglement path And because we're minimizing the surface area, then this creates a curvature. We're minimizing the surface area of the both, which is the entanglement pass spin network, essentially. Is derivative of that n minus one dimension. What the hell is squid even? Movements of the surface. Oh god. Alright, let's look at G induced over here real quick. G induced over here. That is the x mu over partial. Oh my god, what is this squiggle? There's like this crazy squiggle. What's the squiggle? It's driving me crazy. Interesting. Here's the Salita symbol we had before. Almost there. Nevi Civita. That is the Nevi Civita symbol, I believe. Yeah. I'm really hesitant to write this squiggly symbol because I don't know what it means. I'm trying to figure that out right now. this thing again. And it's just a differential volume element. Oh, that would make sense. It's called a differential element. The differential element. So I believe what it's saying. Taking a differential of like one dimension lower, and that creates the surface area or something, which would kind of make sense. Yeah, I mean, you're integrating one dimension lower to get the area. Alright. Squiggly E was just kind of scaring me. So, essentially, we need to get to general relativity using this curvature of entanglement entropy. This is an n plus one dimensional curve spacetime. Relativity boundary. Not too sure what this is right here, but let's look at the boundary. This is the boundary of D-through space. ADS space. Boundary of ADS space is D-dimensional. Okay. Um, okay. we were to do if we were to do a small perturbation of the entanglement entropy, this, that's going to be equal to, I'm going to get some small quantum perturbation in state A, or rather the expectation value of that quantum state, change in entropy. So this kind of shows that it's the entropy and the quantum states. Small perturbation in boundary causes small perturbation in the area, which causes a small perturbation in the metric. So, this again. And, well, at this point, let's just go ahead and relate this to spacetime curvature, where we finally get the Ricci curvature tensor here, minus 1/2 r g uv, and then plus cosmological constant GUV, and this equals 8 pi, 8 pi g, and there's the stress energy tensor. Oh. Spacetime curvature, this of course is the Einstein field equations of general relativity. And it appears that it's coming from minimizing the surface area of these that are basically formed by these quantum entangled paths. It's causing a curvature in the metric, and the reason is because we're trying to maximize entropy, right? But at the same time, we're trying to minimize energy. So maximizing entropy leads to, uh, more entanglements. While at the same time, we're minimizing the energy, so we're minimizing the entanglement paths. Minimize the paths, and therefore you get curvature. So we can see how gravity just naturally arises from minimizing entanglement, entropy, surface area. As we head towards a maximum entropy state, getting more entanglement, keeping the energy as minimum as possible, minimizing the paths, creating more curvature. There are more ways that we can continue to connect these things together, but this is a pretty decent overview. I skipped some things and said some extra stuff, so maybe, there's more details. But the idea is that we've already covered so much and we've related this all together and we put it all into one consistent, cohesive theory. That makes sense. And now we ask ourselves, what is this cosmological constant here? Um, no, just give me a second. Mm, okay, basically, cosmological constant comes from the energy of the fluxes. The energy of the fluxes. Alright, that's the fluxes that are these fluxes. It's basically like the fabric that's holding everything together. Energy of that fabric. I think they put energy of the flux. 1 second. Energy of the flux. Okay. I don't want to go too far off, but we can say maybe something up here. Here's the action of the flux. 1/2 integral e d plus 1 x square root g. This is the determinant, by the way, of the metric tensor. And then we have the fluxes. F P. I'm not gonna worry too much about this. This is just more of just like magnitude of the fluxes. Let's just say it's more like inner product, but inner product. And these are the flux fields that we were discussing earlier. F. Yeah, these. Well, really, it's the three forms. Flux field straights. Jesus Christ. Hmm. These fluxes are getting very complicated. The fluxes are a little weird. Describing the fluxes. That might be a little bit of a challenge. But as we go up a little bit, we have Neveu, the Neveu-Schwarz two form. Here, 1 second. So we have the Neveu. Hmm. Um, these things are the same thing that we're about to just describe again. So they're just different terms because in string theory we say the Neveu-Schwarz, and in the loop quantum gravity we use the Kalb-Mond. Well, regardless, I think it's all for string theory, but this is gonna be the same thing. So where I'm writing it. So let me just ignore all the stuff that I was gonna go into. There's just more names for what we're looking at. More names for what we're looking at, a little bit more complicated notation to describe things slightly more accurately. I think we pretty much have everything. But this, I think, might be supergravity. So the flux energy density is supergravity? This is the 3 form, as we discussed earlier. And then, where's the energy density? This is the action of the flux field. Yes, okay. Don't worry too much about connecting the free form to the two form. It's pretty straightforward. There's derivatives of the boundaries. An action of the flux field in bulk of supergravity theory. This is the energy density. Okay, so I think the inner product is the energy density. Okay. Yeah, so we're integrating that energy density over the space-time volume, which is simply this integral here. This is basically trying to say that this is a volume, all this stuff right here. And this is the energy density, is the inner product, the strength of the fields, I guess. Yeah, integrating the strengths of the fields over the volume. That's the action of the flux fields. This seems to be the cosmological constant. We could really think of it as the vacuum energy of the fluxes. Okay. So I mean, yeah, I mean this kind of makes sense because like think about it. We're trying to like separate real space and time from the imaginary space and time through this flux. It's going to require some energy. Just the idea that we're separating those two from each other is bound to create some sort of, you know, repulsion. Mhm. Hmm, interesting stuff. I mean, this is a unified theory. Mm, Hmm. Just reviewing to see if there's any more little details we can add to kind of solidify this a little bit more. This is like a holographic screen. So this is what happens like in the surfaces of the black holes. This is how they actually manage to figure out entanglement entropy. Oh, okay. This is pretty interesting. Let's just kind of review this one more time. The whole idea is that we're starting with the quantum mechanics here. We've got these wave functions. They exist in a six-dimension complex space. Well, it's really three dimensions, but we need real and imaginary to get six out of them. These are basis vectors. These Hilbert spaces are just tangent spaces to every point. How do we get to this tangent space? We have to rotate through imaginary time to get there. All the Hilbert spaces contain quantum states, entanglement lines, and the wave function convex hull. This wraps around, this can send flux, this basically wraps around and makes fluxes. These flux configurations, the boundaries of the wave functions are strings. The fluxes flow through the strings, they flow through and pass information. And that flux appears to be the 11th dimension, that's imaginary time, because it's entangling everything. And this is how we can sort of get access to the whole universe by going into imaginary time. We see that as we go further into imaginary time, go to infinity, only the lowest energy state remains. We see that the rotations in imaginary time can give us the Hamiltonian action, or the Hamiltonian for quantum mechanics there. And we see how we can start to put all of the Hilbert spaces together and entangle all of those and make a spin network. So that way we can make the spin network of more entangled volumes essentially. In fact, there's a volume associated with the Hilbert spaces. Let me see if I can calculate that volume. The volume of each one of these little Hilbert spaces. Okay, here's the volume. Volume. Give it the volume expectancy value. Alright, so we're going to take the Planck length for the third power. And then we're going to take a sixth of some, and I do believe that this is the Levi-Civita symbol right here again. We're going to go I, J, K, and then we have the J, these are the flux generators. Let's just leave it at that. So we have basically Ji, J, K, or J, I, J, 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 and J, K. I have to send this to the I, to the J, and to the K. Alright. Anyway, we basically find that the volume of these Hilbert spaces has to deal with these flux operators as generators. And these generators, they come from SU2, Lie algebra. I think those might actually be polymatrices, maybe? I think they might be like polymatrices. Yeah, so they're related to the polymatrices. Okay, so anyway, so this is how we get the volume of the Hilbert spaces, which are in fact quantum nodes themselves in the spin network of entangled quantum states, which forms in surface area in the bulk, which is anti de Sitter space. We're minimizing the surface area in this bulk, which gives us the boundary in the holographic three-dimensional screen. That's the curvature. All right. Minimizing that area leads us to this curvature. We're trying to maximize entropy by getting more entangled states together. We're trying to minimize energy by minimizing the paths. And this is all happening through that. The information is passing through that 11th dimension of imaginary time. And that energy, the 11th dimension, seems to be vacuum energy, cosmological constant. All right. Mm, Another very interesting, another very interesting, another very interesting section. All right. I think this is pretty good. Pretty much covered everything we need to see how all this stuff is connected. And very important that the strings are actually just the oscillations of the boundaries of the wave functions. As the wave function makes a surface area, we can look at the boundaries of that surface area, and that's the one-dimensional string oscillates, and it oscillates around the flux information that's passing through. There's just circular loops of energy. See how the actions work together using the world sheet metric and also the flux configurations. And then you can see how they have dualities, and the dualities is just simply trying to say that, well, you're trying to combine wave functions together and, split them apart, and boundaries are really what you're going to see, the interaction of the boundaries. So we've got momentum and position could be described. So you're switching between T-Duality, Superposition duality, or you can figure out string coupling, which is the strength of entanglement. That's going to give you S-Duality. Wow. This is some crazy stuff, but yeah, I mean, it all seems like everything is just different perspectives of the same underlying structure. All we're really trying to do is project stuff from complex dimension into the real dimension using fluxes going through imaginary time. And of course, that's going to cause uh, some this vacuum energy discrepancy, as those fluxes have sort of the vacuum energy, and try to calculate that. There's a little bit kind of where that stuff starts to emerge from cosmological constant. Now we're trying to minimize that surface area to create the curvature in general relativity. Wow. Wow, guys. Just, wow. This is truly some fascinating, strange. Anyway, I call it a day here. Have fun.